Great, thank you. Happy to be here. Okay, don't need your papers. I'm going to try to level set. Who here has heard of TCP SACKs? 3 or 4 or 5 of you. Great. Who here is a Linux networking stack expert? Great, me neither. So who am I? Let's see if I can get this thing to work.
If you want, I can just advance this.
Point this way.
Oh yeah, makes sense. Magic.
I can just advance the slides if you like. Let's just do that. Right.
Okay, sure. So yeah, I am a kernel developer by trade, and I've found my way into big data at Databricks. If you've ever seen the blue screen of death, localized, that's my fault. Don't blame me for the frowny face. That was our UX team. But there were enough complaints that scary message was not localized, so we went and actually localized it. Doing this during a kernel panic to display it in a rasterized font with anti-aliasing is not exactly easy. But anyways, I went from there to building my own OS from scratch. Fun to do, hard to sell. Now I'm at Databricks. Yeah. Okay, so what we're going to do, we're going to talk about a benchmark that we started seeing fail in late June. Kind of why we thought that was related to TCP SACKs, how we debugged it to confirm that it was, and then how do we root cause the problem and blame it on the Linux kernel.
Which version of Spark?
So at Databricks we use DBR, so Databricks runtime.
Okay.
So it's Spark plus our own bits. The interesting part, it didn't matter which version of Spark, because it was an underlying kernel change. So we saw it hit on all versions of 2.3, 2.4, etc. Yeah, there. Okay, so this is the benchmark that we started seeing. It was 6 times slower than normal, and that's not great. So the blue, where you can see the AMI 299, is the AWS image we were using before TCP SACKs showed up, or the regression. Then the 2102 includes the regression, and then back to normal once we've patched it. But this is sort of a shock to be like, we updated the kernel, and Spark starts running 6 times slower. Yeah. Okay, so what is this benchmark? Create a table that's 10 billion rows and write it to cloud storage. Not super complex, not a whole lot going on there. And as I said, it didn't matter which Spark version we were running. As long as you were writing to S3, this could hit. You just needed networking traffic. Okay, so where did we notice that the benchmark was going wrong, right? So looking at the Spark UI, we saw skew in the tasks. So you don't have to know much about Spark. A job is broken down into multiple stages, which might spill the disk, and then a subsequent stage might pick up that information with a sort of like if you're doing a hash join or something. In this case, each stage is broken down into multiple tasks. They do one small chunk. Each one of these is doing one small chunk of that 10 billion rows, writing portions of that to cloud storage. And you can see that one of them is taking 16 minutes. The rest, all finished in less than a second. Or I can tell you that. Well, 17 seconds, sorry. But that's pretty extreme skew. And now it's kind of interesting. It's like, okay, what's going on here? So diving a little bit deeper, we looked in our logs and saw that we had this exception from S3 that a socket had timed out. Okay, well, you'd expect the network to be reliable, even in the face of packet loss in a busy cloud. Why is this socket timing out? So yeah. So before we get back to that, we need to talk about TCP SACKs. So at the time we started seeing this benchmark fail, the TCP SACKs vulnerabilities were disclosed by Jonathan Looney at Netflix. And the Linux community had the patches ready to go. Our customers, out of compliance reasons, etc., wanted us to update our kernel, so we did. Arguably, we maybe should have pushed back and said, okay, is this actually a security vulnerability for you versus performance impact? But we went ahead and patched it. The worst case for these vulnerabilities is that a remote attacker could cause a kernel panic and DOS your machine. Not stealing any data or anything scary like that, they just can DOS you, which is potentially bad for business. And then that was kind of, there was 3 different vulnerabilities. The other 2 were more resource exhaustion, not a straight panic, but they could slow down your system effectively DOSing it. And so the mitigations out there were to update Linux kernel or turn off TCP SACKs. So, I think next. Yeah, so we'll get to why option 1 of turning off TCP SACKs was not really an option. So, if you've ever played around with TCP, this diagram might be familiar. 3-way handshake at the beginning. Sockets in the established state can exchange packets from both the sender and the receiver. And then we kind of have this closing state where maybe only one side is sending data. If the remote sends you a fin, you actually are in this passive state in closed wait, and you can still send data to the other socket or the other end of the connection. Anyways, don't necessarily need to dwell on this. Okay, so TCP without SACKs. So SACK stands for selective acknowledgement. Okay, so without SACKs, this is what happens. The sender will send one segment. The receiver will say, okay, I've got the segment. Then the sender is going to send a few more, 2, 3, and 4. Well, there's packet loss. Segment 3 doesn't actually reach the receiver. The best the receiver can do is say that I got segments 1 and 2. It can't communicate that it actually got segment 4. So as a result, when the sender is going to retransmit the data, it has to resend segment 4. And then once it's achieved, the receiver can actually say, okay, I've got 1, 2, 3, and 4. But this can add up, right? It can add a lot of traffic to your network. You can only say that I got, that packet that was, 1,000 packets ago, and I, got missed one, and then 999 others I actually got, but I can't tell you about it. So, enter TCP with selective acknowledgement. So, same scenario, but this time, after segment 3 is missed, the receiver can communicate that I got 1 and 2, but I also got 4, right? And that can get more advanced as you go along. But in that case, the sender only needs to resend segment 3, less data, less transfer, better performance. Okay, so what might this actual vulnerability look like? So, as a malicious user, the receiver, I can kind of choose what I want to acknowledge, right? I don't need to actually care if I could get all the packets and I could say, well, I didn't get this particular section of, set of packets, right? And so to really take advantage of this, we need to talk about the MSS. So this is like the minimum or maximum segment size that the 2 endpoints can communicate with, which means that each TCP fragment can't be bigger than this many bytes, including the headers. The minimum allowed for that is 48. Well, to account for headers, those are 40 bytes, which means that each packet is left to be 8 bytes long. So, and both sides have to agree, and you have to agree on the minimum. So, as an attacker, I can say, okay, I only can accept 48. So, as a result, the victim has to send really, really small segments. So, a bunch of them, but then here the attacker can say, okay, I'm going to acknowledge every other one. What's that going to do to the sender? So, what might that do? To get there, we need to dive a bit into the Linux kernel. If you recall, my background is in the Windows NT kernel and building my own kernel, so I haven't really been allowed to look at the Linux kernel for a long time. And so I'm sort of 3 months into this, so bear with me. Okay, so what can happen with that sort of maliciously crafted SACKs packet? Okay, so the Linux kernel has socket buffers. So each socket will coordinate its sort of like send queue into a linked list of buffers. Each one of those buffers might have multiple fragments for DMA reasons and other to make it more performant. Those fragments actually can store page virtual addresses and offsets in sizes, so we're not actually having to copy data into a buffer like we did in the old days. We can just say, all right, here's some user web page, pin it, and give it to the socket. As a result, we get a buffer that looks like this, that has up to 17 fragments. Each fragment is some page of memory. That's fine until the selective acknowledgement comes in. And this is where, okay, I got these first 8 bytes, but not the next 8 bytes. So part of the ACK processing wants to fragment these socket buffers so that we can maybe free some because those were acknowledged. So as a result, I might now have a socket buffer that points to the first portion of the fragment 1 that didn't get acknowledged, and then I kind of fragment it to have another socket buffer to point to not bytes 8 through 16, but 16 onward in that fragment, and then the rest of the bytes. Ad nauseum, now I have a bunch of socket buffers, all pointing to 8 bytes. And this list of socket buffers for this particular socket has gotten extremely long, more time processing in the kernel to even send any data, potential DOS if I'm doing this to every connection on a machine. And so that's sort of how I think about how this attack might go. Go try it at home. Just make sure the kernel isn't patched. But this is the resource exhaustion attack. It's not the panic attack. To actually set a kernel panic attack, kernel panic, we can talk about that one after if you want. So, looking at this one, we noticed that the Linux community got it wrong twice. So the initial patch went out June 17th when the vulnerability was announced. 4 days later, they said, okay, I need to tweak something. And then not until almost a month later, they're like, oh yeah, we forgot this other case. And so between the 21st of June and July 19th, Databricks was sort of struggling of like, what is going on? Because this is not Spark. If we roll back the kernel, we're fine. We kind of take for granted that the Linux kernel is giving us the stable foundation, and it's great for what it is. But this was sort of chaos. And so on the 19th, when I actually saw this patch go up to mainstream Linux, we're running Ubuntu 16.04, migrating to 18.04 as we speak. Ubuntu hadn't published anything, so we went ahead and tested out a patch, backported that thing, applied it to our benchmark. The benchmark was clean. So once we had that third patch, we knew we were going to eventually be good and not, wading through more TCP issues. Okay. Yeah. So given this information about TCP, and if you remember back to the skewed task information, the timing seems right, but can we actually blame TCP SACKs for what we are seeing? So yeah, as I said, it didn't matter which version of Spark, and reverting the kernel, just the kernel seemed to fix the problem. So all the layers of code on top of it in the Databricks stack seemingly were not to blame. Okay, so given that we had a benchmark that reproduced this consistently, we actually jump on a live repro and dig in here. So once we kind of saw that this Spark stage was taking longer than 20 seconds or so, we were able to jump in the Spark UI and figure out which task was still running, that skewed task that was going to take just over 15 minutes. And so from that, I was able to get the IP address and jump onto the machine to try to figure out what was going on. And so the tool I knew to use was Netstat. Okay, so what's going on? Is there a socket that has maybe sitting around for a long time? And so monitoring Netstat, over a few minutes, I kind of saw that this particular socket that was in the closed wait state, if we go back to our diagram, was just sitting there, right? And closed wait again means that the remote side said, I'm done, I'm not going to send you any more data. You can send more data if you want. And so this socket clearly had 98K bytes waiting to be sent. And so this one was in that state, but seemingly not sending more data. Okay, so after some digging, one of the lessons learned here, I found this SS tool. So I was like, Netstat's not giving me enough. I know there's more to a Linux socket than the send queue and the receive queue in its state. So SS actually turned out to be a really powerful tool. You can look at all of this socket information that the the socket structure holds. And so there's interesting things here, like all of this memory tells you the write queue, the receive queue size, etc. But for this case, this particular socket, it hadn't sent any bytes over the wire, nothing, for just about 9 minutes, or almost 10 minutes, which was super surprising given that the retransmit functionality in Linux should be wait 200 milliseconds, try again, wait 400 milliseconds, try again, exponential back off. I wasn't seeing that because no data was going out. And up there, the timer is telling me that we've actually tried to retransmit 13 times, but nothing was being sent. That's super weird. So yeah, this is sort of the how it adds up to the just over 15 minutes or 16 minutes we were seeing in the Spark UI. If you do exponential backoff with the TCP retry mechanism, starting at 200 milliseconds, maxing out at 120 seconds, after your 15th try, before you quit, you've waited 15 minutes and 24 seconds. Or a month, yeah, 15 minutes and 24 seconds. So that's, hey, it's seeming great. We've kind of have a culprit and we can explain what we were seeing in the Spark UI. Okay, but I'm not done. I wanted to know what was actually going on at the packet layer to be like, okay, well, this one tool was telling me it wasn't sending data, but the TCP dump, maybe there's something in there. Oh, what did we find? We have SACKs, so okay, maybe that's to blame, maybe that's happening here. And so this is the connection where we sent 1.4 megs or something, and then dropped 21K, which would be between the ACK and the left edge of the SACK, because the SACK is saying which data it actually received, right? So it got up to this point and then actually everything after, because this right edge kept increasing. But after this first SACK to say that bytes were dropped, there was silence on the TCP dump. 40 seconds, when I've expected 7 retries because of the retransmit. So again, kind of corroborated the evidence that SS was correct, that no packets were being sent over the wire. So this connection dies, goes into the closed wait state, confirming what Netstat saw, because the remote side sent a fin. And so what we end up is 21K of unacknowledged bytes and about 76K of selectively acknowledged bytes. Add these up, that actually magically added up to that send queue that we saw in Netstat. So, oh man, the world's aligning. So the weird thing is, right, we actually selectively acknowledged, or the remote side acknowledged 77 or 76K, right? Why weren't those bytes freed? So that's kind of a second question that came up here. Like, they were ACKed, why weren't they released? And that was, so I kind of had two questions. Yeah, two questions. So why are the retransmissions failing? And then why are those sacked bytes not getting freed? You know, maybe my misunderstanding of the Linux kernel could answer some of the parts of the second question, so I was hoping somebody in here was an expert, but kind of the theory. So if you remember those 3 patches that went out, the initial fix, the second fix, and then the third fix, they were all in this function, TCP Fragment. So if you remember back to the earlier slide about breaking up a socket buffer, that's what this function does. It basically says, okay, I have a socket buffer, carve off the first n bytes, keep that in that buffer, and make me a new one that has everything greater than n. And clearly that can be bad if we fragment too much. We might run out of resources or cause a kernel panic. So that's what this line went in for, to saying if there's more memory queued than what we actually intended. So this send buff is actually what you can set in a socket opt, and it defaults to 64K, saying like each socket shouldn't have more than 64K bytes pending, waiting to be sent. But the Linux kernel actually can overshoot that by 64K. And so as a result, they kind of wanted to allow some fragmentation, but not the crazy fragmentation that the TCP SACKs vulnerability can expose. And so that's why that went in. And then this was just a corner case that they were trying to handle. It didn't actually end up being an issue for us. But the big kind of indication that we were actually hitting this if condition was the nice stat that they threw in. And on the executor that was failing with the skew task, we actually saw that value being pretty high when we looked at nstat. Okay, so first question, why is the retransmission failing? So if you look at the retransmit code in the TCP stack, you see this if statement. So if the socket buffer's length is greater than the current max segment size. Here we had a normal max segment size, so S3 was not actually a malicious attacker, thankfully, of 1412 bytes. And I strongly believe that I don't actually have the data to say that this socket buffer was greater than 1412 bytes, but given that we have TCP segmentation offloading in place, which basically says, let's not, in software, break up a TCP packet into 1412 byte segments and send one at a time. Let's put a big chunk down to the hardware, let the hardware split it up, and send out separate packets, add headers, checksums, etc., and send those over the wire. And so when you're dealing with that feature, when that feature is enabled in the Linux kernel, your socket buffers actually should be greater, closer to 64K or something would be the initial start, where they're allowed to grow to be that big. And you can imagine that your initial writes are very contiguous, so you can have a socket buffer be that big. Obviously, as data gets dropped, you might fragment them, the whole problem. And so in this retransmit queue, I guess this tries to actually fragment it. And what we're doing is saying, for the socket buffer, carve off the maximum segment size. So for whatever reason, I guess TCP offloading isn't necessarily trusted or something in the retransmit case, because we're actually going and creating a smaller socket buffer that is just the size of that MSS. But, of course, if TCP fragment fails, we give up. Hard fail, don't try to retransmit anything else, just wait until the next attempt and hope we succeed. But we weren't, and we never were going to. So again, back to this code. The Linux commit message that put that in there, that's where I kind of got this, that the mem queue, which is all the memory queued up to be sent, all the bytes queued up to be sent from this socket, can actually overshoot what is supposed to be the maximum because of TCP segmentation offloading. And so, okay, it's possible. The Linux TCP experts say, yes, this could be the case. And what I was actually seeing from SS was that it was the case. The WMEM queued was well over the size of skbuff, just about 64K over. And so as a result, when we do the division by 2, we actually hit in this if condition. And so we can prove that our socket information shows that if we got to this if condition, we would have returned true and failed to fragment. So given that we're seeing this stat and we have the socket information from SS, I can say confidently that we're actually hitting this if condition. And that was causing the retransmit to pop back up and not try, and actually sending no data over the wire, which we've corroborated with the TCP dump and SS as well. So then the second question of 76K bytes were selectively acknowledged, why weren't those freed? Well, in the ACK path, when we were handling a TCP ACK, we also try to fragment socket buffers. And so somewhere in this stack, or down this stack here, we call TCP Fragment. That's going to fail for the same reasons. And so as we pop back up that stack in TCP shift SKB data, that just does a hard work again. Oh, I failed. Okay, we'll try again later. But we've got two sides failing. We're actually never going to succeed. And so this socket ended up actually being hung it was not able to free any data to release the memqueued size, to reduce the memqueue size, and it wasn't able to retransmit any data for the same reason. So in comes the fix. So this is the third patch. And so what they did was realize that we can actually overshoot W memory by 64K. So let's bump up the tolerance on that size of W mem queued. And they bumped it up by 128K. And so once we took that patch, we no longer saw the TCP SACKs regression. That same benchmark went back to normal as it was yellow on the second slide. Yeah. So, what did I learn? Or what did we learn? Because it wasn't just me. Consider the whole stack. So, as much as Spark is sort of this battle-tested thing, we were like, okay, well, we're making changes in Spark. Maybe we broke this, and we have a whole platform that delivers, Databricks' version of Spark. So, clearly there's something in there that we broke because this coincided with an update to the platform. I think thinking that it was Linux was last on our list, just because that's that stable bedrock of all of our cloud infrastructure at this point. Turns out that Linux, can get things wrong as well. And in fact, we've seen two other issues more recently. One is sort of a regression when you have unprivileged containers using overlayFS. We talk about that one. And the other one is hung writes to ext4. Has to do with ext4 lazy init. Don't know yet. So future blog posts on that one. And then the second was sort of this benchmark that we had was just a number, right? It just said something's wrong. It didn't really tell us what was going on, right? There was a lot of debugging that went in afterwards to, root cause the issue. But the initial logging that said, okay, socket timeout was super useful. So, I think the iteration there would be to have the benchmark, but also, surface the errors that it's seeing while it's failing to maybe reduce the time to diagnosis. And then, know the tools you've got to use. So I didn't stumble upon SS until a couple weeks into it, and that just was like light bulb. I can actually see what's going on with the socket. That's sort of it. Sort of adventurous debugging the TCP stack.
Thank you so much. Awesome talk. Really, really great slides. We can take a couple of questions, and if I can have the next speaker come up and set up the laptop. I only have one mic.
So other than the network error, were you able, what helped in narrowing it down to the Linux level?
Yeah, that's a good question. So this was actually like we have Databricks is cross-geo, so we have a team in Amsterdam that kind of works on our performance cases, and since this was a Spark performance issue, it hit them first. I work more on the back end, like cluster management side of like making sure Spark clusters are reliable. So like compute auto-scaling, disk auto-scaling. I seem to debug network problems.
You could see GC time.
Right. So what else? The question was what else was going on?
Yeah,
right?
other than the network timeout.
Yeah, and so I think what ended up